listening to With Electronics What's Up Radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our very own Worth Electronic technical specialists. We're going to shine a light on our topics like energy harvesting, wireless power transfer, EMI issues, and more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast. When designing a circuit, one of the main considerations you need to take is the expected lifetime, not only based on the product itself, but also the individual components included. When considering the components themselves, some of them can fail completely or degrade in performance in time. Now, for optocouplers, the performance, which is current transfer ratio, degrades over time depending on the operating conditions. In today's podcast, we'll start by giving a quick introduction into how Worth Electronic tests its lifetime of its optocouplers and how you can calculate the expected lifetime of your application. We'll also give some special tips and tricks into how to operate the optocouplers for increased lifetime. So let's start with the basics and a brief history lesson. Today, optocouplers are widely used in power supply, home appliances, industrial control, and other regulating and controlling applications. Back in 1963, optocouplers were invented at IBM as isolation devices, and they've really come a long way from its origin as a simple light bulb coupled with a photoresistor. Maturing technology of solid-state light sources, such as the LED, have led to a miniaturization of the optocoupler and its wide usage in industry as an isolation device. Today, most typical optocouplers consist of an LED that's optically coupled to a phototransistor, photodarlington, or phototriac. From the beginning, the lifetime of the LEDs was an issue, and even though the reliability of LEDs has steadily increased, it's still worth taking its lifetime into account when considering optocouplers for applications. The major root causes of failures in LEDs can be separated into two different problems: die bonding related failures and package related failures. Package related failures, which appear as early life failures, are a result of fabrication errors or even mishandling. Examples of those include wrong soldering profile, increased humidity during soldering, or temperature-induced stress on bonds, such as thermomechanical stress between bonding wires and transparent epoxy, which seals the LED. Die-related failures or degradation, which affect the lifetime of LEDs, those are related to thermal management during operation, which is in direct relation to the nominal current of the diode and heat dissipation. Thermal stress in the LED's junction zone results in lower light and therefore has a direct impact on the component's efficiency or CTR factor. Today, we're going to focus on the long-term failure of optocouplers, and that's related to the decreasing light output of the LEDs with time because of long-term operation and accompanying failure mechanism. So in this case, a form of the so-called electromigration. The simplest optocoupler consists of an LED optically coupled to a phototransistor, but being electrically isolated from each other. The LED is turned on and off to emit light, which switches the phototransistor on or off. An important parameter describing the optocoupler's performance is the current transfer ratio, or CTR. It is defined as the ratio of the current flowing through the LED and the current flowing through the phototransistor. In the Worth Electronic optocoupler portfolio, you have the option to choose ratios from 50% up to 600%, divided into different range bins depending on the customer's application. Now let's talk about the lifetime testing. The lifetime of optocouplers can exceed several decades, so this means that we need an accelerated stress test using increased operation conditions. In semiconductors, many different degradation mechanisms exist. Some of them are the electromigration, nucleation, and growth of dislocations and metal diffusion. These degradation mechanisms can be described with specific activation energies, which can be viewed as the energy required to activate this failure mechanism. Depending on the specific mechanism, this activation energy varies between -0.2 and 1.4 electron volt. For LEDs, high current density and high temperature leads to diffusion of atoms out of high active region, leaving point defects. These crystal defects increase the number of non-radiative recombination centers, thus decreasing the quantum efficiency of light creation and decreasing the CTR of the optocoupler. This mechanism can be described similar to the electromigration of the atoms originally described by J. Black back in 1969, and this is where he described the median time to failure of a device. You can see this equation as Figure 1 attached in this podcast. This formula is described as 1 over MTF equals A times J squared times e to the negative E sub A divided by K sub B times T. Now, where MTF stands for the median time to failure, A is a constant, including scattering across section area, J is the current density, E sub A is the activation energy, K sub B is Boltzmann constant, and T is the temperature in Kelvin. For reliability testing, it is of great interest to reduce the stress testing time by being able to predict the resulting lifetime under normal use conditions. According to our equation, the MTF reduces the current density and the temperature. When testing optocouplers with increased temperature and current, the degrading mechanisms happen much faster than they would under normal operation conditions with smaller temperature and lower current. Therefore, an acceleration factor has to be calculated by dividing equation with stress test conditions and normal operation conditions, and this is widely known as Black formula. Now, as we mentioned before, there is a mixture of different failure mechanisms and corresponding activation energies. The effective activation energy can be found as a fit parameter from repeating stress tests at different temperatures. However, to comply with industry standards, an average activation energy of 0.7 electron volts is used as a typical value for discrete semiconductors. The application of this formula is demonstrated for a series of Worth electronic optocouplers, and those were tested for 1,000 hours under increased temperature of 100 degrees Celsius and an LED forward current of 30 milliamps. The phototransistor is less prone to degradation than the LED. Therefore, it's assumed that the change of CTR is due to the loss of luminosity of the LED and not because of phototransistor degradation. Let's try an example of the acceleration factor calculation and its application to stress test results as shown. The test duration is 1,000 hours at 110 degrees Celsius and an LED forward current of 30 milliamps. If the optocoupler is used with 100% duty cycle at a forward current of 5 milliamps and is operating at ambient temperature of 80 degrees Celsius, then the acceleration factor is 218. So according to the Black formula, the acceleration stress test of 1,000 hours simulates a normal field use of almost 25 years. In Figure 2 of this podcast, we see the CTR degradation that is expected within these 25 years. We can see that Worth electronic optocouplers experience, on average, no more than 5% degradation of the CTR value. The average of 2 sigma, or 2 times the simple sum relative CTRs, are also given in our Figure 2, and those are as dashed lines. Statistical contribution gives the variance 2 sigma as the amount of variation in the data. So in other words, around 68% of the relative CTR values are inside of 1 times sigma distance from the average value. Similarly, 95% of the relative CTR values is within the 2 sigma confidence interval. When considering this, the 2 sigma curve shows the lowest expected relative CTR degradation is not less than 87% within 25 years. And then in our final figures 3 and 4, the average CTR degradation is shown in dependence on the normal operation forward current and the normal operation ambient temperature. Now, it's important to note that the expected CTR degradation can be reduced by reducing the operation temperature and driving forward current of the LED. In figure 3, we used 100% duty cycle, 80 degrees Celsius ambient temperature, and forward currents indicated in the graph. The stress parameters were measured at 1,000 hours, 110 degrees Celsius test temperature, and a forward current of 30 milliamps. In figure 4, it shows the temperature dependency on the expected average CTR degradation with field time. The parameters here include 100% duty cycle, a forward current of 5 milliamps, and ambient temperature described in the graph, but the stress test parameters include 1,000 hours test, 110 degrees Celsius test temperature, and a forward current of 30 milliamps. In summary, optocouplers, as with all other components on the electronic board, need reliable performance for many years in harsh applications such as industrial control as well as power supplies. As the reduction of the LED's performance is one of the mechanisms leading to a degradation of current transfer ratio in optocouplers, it's worth describing and understanding this effect. So Worth Electronic performs extensive quality tests to provide products with outstanding reliability as well as performance. Given the reliability data provided and the presented equations, here are some design guidelines we suggest to increasing the lifetime of optocouplers. First, decrease the effective operating time of the optocoupler. Second, decrease the operating diode current and power dissipation out from the LED by larger vias and pads in the layout. Next, avoid peak transient currents through the LED. And finally, adjust the duty cycle of the LED in order to keep the average current low. In case of critical products regarding reliability, such as devices with medical application, reliability of the optocoupler can be increased by a burn-in procedure. But to avoid damage of the devices, the burn-in parameters should be kept below the absolute maximum ratings. Keeping these rules in mind, the designer can expect a high stability of Worth Electronic optocouplers performance for years to come. Attached images are available in most podcast streaming networks. To view all images, visit www.we-online.com/podcast. You can find the entire lineup of Worth Electronic optocouplers and download the datasheet available at Worth Electronic Online. To download the complete application note discussed today, click the link available in this podcast or visit us online at www.we-online.com/appnotes. You're listening to Worth Electronics What's Up Radio Podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists. We're going to shine a light on our topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up Podcast.